Science Physics. I'm Mrs. Bolden, and today we're going to talk about collisions. How exciting. So the main idea of this section is kind of building on the idea of conservation of momentum that we talked about in the previous video. In that video, we said that before an event happens, whatever the momentum of the objects involved is going to be exactly the same as the total momentum of the same objects after an event. And today, we're going to talk about those objects when we talk about collisions. So the main idea is just kind of a restatement of the law of conservation of momentum by saying when objects collide without any external force. Now remember, physics people love to exist in a fairy world of physics when only certain things apply, and this is one of them. So there's no external forces. The net momentum of the objects before a collision is equal to the net momentum of the objects after a collision. I just want to remind you that net means after the momentum after all the pluses and minuses have been worked through. Whatever's left over is considered net. It's kind of like when you get your net pay. In your first paycheck, you get so much money per hour that you worked. That is your gross pay, and then they take out the taxes and Social Security and things like that, and whatever you have left over, which is actually what you can spend, is your net pay. So net kind of means the same thing in this situation where you have a certain momentum, you have some positive momentum, negative momentum, and then when you put them together, the overall outcome is the net momentum. Okay, so collisions of objects clearly show conservation of momentum. And this is kind of a formula kind of thing that describes the law of conservation of momentum. So the net momentum before the collision has got to equal the net momentum after the collision. You can imagine a car that's coming down Madison Avenue, going down there, it has a certain velocity, which means it has a certain momentum, and then it hits a car at the bottom of the hill, which has no momentum. So the total momentum of the system before the collision is just the car that's moving, and then after the collision, the momentum from that car that was moving gets spread out between the two cars, and each of them have a little bit of momentum, but you can add them together and it will equal the momentum of the car that was coming down the hill that was actually moving. Okay. So at the beginning, when we started talking about momentum, we talked about this little guy here. This is Newton's cradle, and you probably have seen these. There's usually 5 or 6 of these little balls suspended from a frame, and this is all about the conservation of momentum. So you pull this ball backwards and then you let it go, and the momentum that this ball has, because it's in motion, gets transferred to the next ball, which gets transferred to the next ball, and the next ball, and the next ball, until the very last ball swings out, and then it comes back down and starts all over again, going in the opposite direction. That's a great example of momentum being conserved through multiple collisions. Okay, so the first type of collision we're going to talk about is an elastic collision. If you've ever seen somebody playing pool, you have a billiard ball hits a ball at rest. Like if you're breaking the triangle full of balls, with the cue ball, you want to hit that square on that very first ball, and that momentum will be transferred through all the other balls and all go in different directions. After you've broken the arrangement of balls, then you can, and if people are really good at playing pool, they can use the cue ball to move another ball in the direction that they want, and the cue ball will strike the other ball, the cue ball will stop, and then the other ball will continue on with the same velocity. That works because momentum is conserved in that collision. The momentum got transferred from the cue ball to the other ball, and the cue ball now has a 0 momentum because it's not moving, and then the other ball picks up with the same velocity. So momentum gets transferred from the first ball to the second ball in that situation. And if you want to watch a little video on it, there's a little video right there. There's the address. I know it's kind of a weird address, but if you're curious to see this billiard ball collisions in slow-mo, that's a video for you. So an elastic collision is when objects collide without being permanently deformed and without generating any heat. There aren't that many truly elastic collisions. Like usually when you think about cars colliding, there's usually some sort of deformity that happens to one or the other of the cars. But a truly elastic collision, there's no permanent deformity, no heat generated. So the way I try to remember what an elastic collision is, the colliding objects are not hooked together after the collision. That would be considered a perfectly elastic collision. And most of the time when we're doing math problems, we're going to be talking about perfectly elastic collisions. So you have two objects before the collision and two objects after. They don't get stuck together in any way. So here's a scary big formula. Now don't get all freaked out about this. It's just, this is one object here, m1, v1, the mass and the velocity of the first object, and the mass and the velocity of the second object. So you calculate the momentum of this one, you calculate the momentum of this one, and add them together. That's going to be the net momentum before the collision. Back a few slides when we had net momentum before equals net momentum after. This is just a formula to help you to calculate what the net momentum is before and the net momentum after. So they collide, and the momentum of the first one after and is added to the momentum of the second object after. Now you're like, well, this doesn't make any sense. Well, what will happen here is the masses will probably stay the same, but the velocities will change. For example, if this object were going 4 meters per second and this object was just sitting still, after the collision, V1 is going to be 0 and V2 is going to be 4. So the numbers are going to change. I want to put in a pitch now, and I've been talking about it for a while, that if you are not a fan of writing down what you know in the 6 boxes that I give you to do your math problems, you need to get on that bandwagon, because you see there are going to be lots of masses, lots of velocities to do these problems, and it's going to be really easy to get mixed up. So you should get in the habit of, this is the first object, this is mass 1, this is mass 2, and put that in the known box on your problem solving, 5-part problem solving boxes. Okay. So here's some examples of some elastic collision. This is the one that we were talking about before. This little purple arrow represents the momentum of the object. So this red ball has all the momentum. The white ball has none, and we know this because there is no arrow over the white ball. The white ball is sitting still, so it can't have any momentum. So when they hit together, notice what happens. The momentum gets transferred from the red ball to the white ball. The second is when you got two moving balls coming at each other from the opposite direction. And this one's a little more difficult to see because they have the momentum being exactly equal for the two balls. If I were going to do this, I would actually make the white ball have a shorter or smaller momentum than the red ball, because then you could see when they collide, the momentum of the red ball is actually what the momentum of the white ball was. So the white ball transfers its momentum to the red ball, and the red ball transfers its momentum to the white ball. So, and the third one is when you have a fastball, a ball with a lot of momentum and a ball with not very much. The one with a lot, the red ball overtakes the other one. The momentum of the white ball gets transferred, oh, hello, go back, gets transferred to the red ball because the smaller momentum arrow gets transferred, and then the bigger momentum of the red ball gets transferred to the white. So there's a lot of transfer of momentum here. The other kind of collisions is an example of these collisions would be like if you had a bowling ball that was rolling along and it rolled over a piece of chewed gum and got stuck together. So these are inelastic collisions. When the colliding objects become distorted or generate heat during a collision, it's an inelastic collision. I think of inelastic collisions when things get stuck together, like when they're putting train cars together in the train yard. I can't remember what it's called. When they're putting them together, what they do is they slam one car, they get one car rolling and have the other one stationary, and then they hit them together, and then they couple and stay stuck together. So momentum is conservation holds true even in inelastic collisions. That is kind of like a big, because the law of conservation of momentum is a law in science, and laws in science are a big, huge, hairy deal. So it's not just going to be like in one particular situation, it's going to hold true in all situations. So a totally inelastic collision is if the colliding objects tangle or get stuck together. So that's going to be like your big key is looking at what happens to the two objects in the collision after the collision. If they get stuck together, it's inelastic. If they don't, they remain two separate objects, then it's an elastic collision. And here's our formula. We have the momentum of the first object before plus the momentum of the second object before. And then because the objects get stuck together, they now become one object. So we have to add their masses together. And because they're only one object, they're stuck together and they go rolling off like together, they only have one velocity because it really becomes just one object. So this one is a little easier to do mathematically, but you have to recognize the fact that the two objects are stuck together, so the masses have to be stuck together when you're doing the after situation here. Okay, so there's a whole bunch of videos there if you want to watch them. Not really a big deal. There's a lot of different collision videos, but I guess that's it for this time. Thanks for joining me. Have a great day.